We're using a special operator to end our if statements. It's called an else statement, and here we see it being used to specify what to do when none of the other conditions are met. Measure some strings by iterating over the items of a sequence, like this, using a for loop. Looping over a copy of the original collection makes the modification step-by-step and easier to predict, allowing us to avoid accidental deletions. It generates arithmetic progressions for us to use whenever we need a sequence of numbers to work with, and here it's creating one starting at 0 and going up by 1 until it reaches 4. Starts with the numbers in the output list. The variable a is assigned a list of 5 words, and then we iterate over each word in that list, printing its index along with the actual word it represents. When we just print a range, it defaults to starting at 0. So in this case, range 10 actually means start at 0 and end at 9. The sum function is adding up all the numbers from 0 to 3. We use a for loop to iterate over all numbers from 2 up to, but not including 10, and within that, we have another inner loop that goes through all numbers from 2 right up to whatever number we're currently at in the outer loop. The loop is checking each even number in a sequence, and when it finds one that's not even, it prints an odd number. This loop only prints that 9 is a prime number because it completes its final iteration after finding a factor, so we don't get to see the else clause being executed. The pass statement does nothing. It's used here to fulfill a syntactical requirement because the program actually doesn't need any action to be taken in this loop. We're defining a new class called myEmptyClass. So let's use the colon at the end of this line to indicate that it's starting a class definition. The pass statement is used as a placeholder when we're still figuring out how to implement some new function or conditional logic. So here it simply does nothing and gets ignored silently. Watch as it quietly slips away without doing anything. We're using an ellipsis literal to define a match statement here, and it's being used conventionally as a placeholder body. Watch, HTTP error, return, something's wrong with the internet, on screen now that we've typed case underscore. We're using a special word called a pattern here, and it's actually just a bunch of numbers that act as a wildcard to match anything. The pattern binding variables is used here to create different branches of execution based on the values in the point tuple, and it's matching a tuple against all possible patterns before raising an error if it doesn't match any of them. The underscore init underscore method is used to initialize the attributes of an object when it's created, and in this case, it takes 2 values, x and y, which are then assigned to the object's attributes. We're defining a class that matches points in the coordinate system and using positional parameters to bind attributes to variables. The underscore match args underscore variable helps us understand which variables are being matched by providing a list of attribute names that would be used to access the object's properties. We can add an if clause to a pattern known as a guard, and in this case, that guard is x equals y. A special unpacking pattern is used here to assign values from the match object, capturing one of its elements into a named variable. When we run this pattern and someone enters green, it should print out grass is green, as expected to appear on screen right after the corresponding case statement. We're defining a function that takes one argument, n, and prints out all Fibonacci numbers less than n. So let's start by creating this function, which we'll name fib. Now we need to generate the sequence of Fibonacci numbers. The function name, fib, is introduced, which will be associated with a user-defined function object in the current symbol table. Fib returns none implicitly when it has no value to return explicitly. We're defining a function that builds up a list of Fibonacci numbers on the fly and returns it, starting with two initial numbers 0 and 1. We're defining a function called askOK to get confirmation from the user about some action, and one of its parameters is named reminder. The function will print this reminder if the user's response isn't valid until it reaches 0 retries and raises an error. The variable I has a value of 5 at the beginning, but is then reset to 6 before being passed as an argument to function f. As expected, when f runs, it prints out this old value of I, which was 5. This function is using a default argument. Notice how the list L is being reinitialized on each call with an empty list as its value, which affects the output because we append to this same list L for all the different values of A. We need to ensure that the list isn't shared between calls by making it default to an empty list when not provided. Functions can be called with keyword arguments, where you specify a value for each keyword, like voltage and action in this parrot function. This function can accept a voltage value and 3 additional parameters for state, action, and type, which it receives either positionally or via keyword arguments, as shown when we call parrot with different combinations of positional and keyword values. The power operator is used to indicate that some parts of the code are being executed, which makes these function calls invalid because they're missing required arguments or have incorrect syntax and values. We're passing keyword arguments after positional arguments because they can appear anywhere within a valid set of arguments. The function takes a dictionary of keyword arguments after arguments. Watch that dictionary being unpacked into the keywords variable later on, containing all key value pairs except for those corresponding to formal parameters. We're using a function called cheese shop to create this example. It's printing a message of apology to the customer. By default, arguments may be passed to a Python function either by position or explicitly by keyword, which is why we're using both positional and keyword-only parameters in this definition. A function where parameters are being marked as positional only, which means the order matters and they can't be passed by keyword, indicated by the / in this case. The power operator in Python is used to call a function, and it's being used here to invoke standard arg 2 different ways. Since positional-only parameters cannot be used as keyword arguments in Python, we're seeing a type error when trying to pass an argument using its name instead of just its value. Watch for arg show up as an error message on screen. Since we're allowing keyword arguments here, when we pass in a value, like 3, it gets added to our dictionary instead of being given as an extra argument. The function is using these different calling conventions to accept arguments in unique ways, but it's showing us an error when we pass too many values at once because of its positional-only argument. A positional argument can be confused with keyword arguments when using double asterisk syntax KWDS, which has a name as a key, and that's exactly what's happening here where name is both an argument and a key in KWDS. The power operator is used to unpack a dictionary into keyword arguments, but in this case, it's causing trouble because we're trying to bind a value to a positional argument, which doesn't work that way. Using positional arguments alone is allowed, which allows us to pass a name as an argument and also use that same name as a key in keyword arguments, like we see here when foo accepts a single number, but then a dictionary that includes name. The power operator is used to group keywords in Python, and here we see it being used after the parameter definition to clarify that POS or KWD can be passed as a keyword argument without causing confusion about its meaning. We're using a variable number of arguments here, indicated by an asterisk, to handle any number of items that need writing to a file, allowing for flexibility and convenience in our function definition. The *args parameter is used to capture any remaining input arguments that are passed to a function, which means it gathers all extra values beyond what's explicitly listed. We can use the * operator to unpack the arguments out of a list or tuple into separate positional arguments for a function call, as seen in this example, where we take a list of 2 values and pass it directly to the range function. Dictionaries can deliver keyword arguments with the operator, which unpacks them into named parameters for function calls like this one. We're defining a function called makeIncrementer, and it's creating an anonymous function using Lambda. Watch how 42 shows up as part of this new function. We're sorting pairs of numbers and words using a Lambda function as the key, so we can sort them alphabetically by the word instead of the number. We're adding a docstring to our function using triple quotes, and we've specified an example of how it should look by including a summary line that starts with a capital letter and ends with a period. Function annotations are stored in a dictionary as part of their metadata, so when we print the function's annotations, what appears is this exact same dictionary that contains the type information used by the function and its parameters.